Welcome to today's webinar, The Power of CONVERGE for Race Engine Development at Roush Yates Engines, brought to you by Convergent Science and Roush Yates Engines. Thank you for joining us today for the 8th event of the 2025 CONVERGE webinar series. My name is Mattia Sulis and I'm part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear from our partners at Roush Yates Engines about their latest work with CONVERGE. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. Roush Yates Engine designs, develops, and builds over 800 engines per year in partnership with Ford Performance. Roush Yates Engines is the exclusive engine supplier for Ford's NASCAR Cup and Xfinity Series teams since 2004. In total, Roush Yates Engines has won over 475 races in NASCAR, IMCA, SA, and WEC racing series, including 40-plus championships. Through dedicated employees and constant pursuit of power, performance, and reliability, Roush Yates Engines was recognized as Top 10 Engine Builder of the Decade. Now it is time to introduce our speaker for today's event, Jamie McNaughton. Jamie McNaughton serves as the Technical Director at Roush Yates Engines, where he leads the technical engineering and strategic direction for all powertrain programs. His expertise drives the design, development, and testing strategy for the NASCAR Ford FR9 V8 engine platform, used in both the NASCAR Cup and NASCAR Xfinity Series, in partnership with Ford Performance. Under Jamie's leadership, Roush Yates Engines has won the last 3 NASCAR Cup Series Drivers and Owners Championship, making the first consecutive three-peat in Ford's 75 years history in NASCAR. Behind NASCAR, Jamie's provide technical leadership engineering to support Ford's highest performance lifestyle sports car. The most recent example would be the heart and soul of the new Ford GT Mach 4 at 1.7 million car, with its just 6-7 end-built cars produced. The number pays homage to the original NK4 victory at the 24 Hours of Le Mans. The car features a meticulously engineered twin-turbo V6 EcoBoost engine, delivering over 800 horsepower and 680 pounds-per-foot of peak torque on 93-octane pump fuel. Prior to joining Roush Yates Engine in 2013, Jamie had led the design and development of several production and race engines programs while working at Ford Motor Company and Harley-Davidson Motor Company, which took him around the world to Austria, Italy, Germany, and India. With over 30 years of motorsport experience, Jamie is passionate about the challenges of competition, teamwork, and winning. Jamie earned his undergraduate degree from University of Michigan and his master's degree from University of Wisconsin-Madison. During today's webinar, if you have questions for the speakers of the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, it is now time to start. This is a quick video introduction to Roush Yates Engines, and after that, we will hear from our speaker. Thank you.
Good afternoon or good morning for some of you. My name is Todd English. I'm going to run us through kind of the company history at Roush Yates Engines, then I'll turn it over to Jamie McNaughton. But we have been partners with CONVERGE CFD software since 2016. How do we get here? So prior to 2004, Jack Roush and Robert Yates had their own engine development companies, one located in North Carolina, one located in Michigan. And Jack and Robert were like brothers, and they were brothers to Ford Motor Company. They wanted the resources, they wanted the allocation of technology, and they really battled each other on and off the racetrack for many years. At the end of 2003, with the leadership of Ford Motor Company, we understood that the business, the landscape was coming. Toyota was even coming. So with the encouragement of Ford, you had two legendary, iconic NASCAR Hall of Fame engine builders merge their operations at the end of 2003 and begin in 2004. When we first started the company in 2004, we had 64 employees. Today, we're about 225. Throughout the years, again, I mentioned we started with the Cup side of the business, moved into Xfinity, moved into truck, also started building V8 engines and V6 engines for Daytona prototypes, moved into some other series. In 2010, you can see we actually started adding different teams with Front Row Motorsports and Petty in 2010 to our Cup program. Just going through some various slides here, but 2009 and 10 was critical as well as we introduced the Ford race in 2009. That is our NASCAR Cup engine that we race today. That has obviously changed in development for many years. Another highlight with Roush Yates Engines would be in 2016 when we partnered with Ford as well as Chip Ganassi Racing to go back and compete on one of the iconic racetracks in racing, which is Le Mans. So being able to showcase to this community, we do have various engine platforms and programs. A lot of that is dependent on Ford Motor Company and direction that they would like to race. Here, most recently, it's been a few really good years for us on the NASCAR Cup side with the NASCAR Next Gen program. We have won the championship in the last 3 consecutive years in 22, 23, and 24. And look forward today, currently have 3 NASCAR race car drivers in the championship hunt. Just high level where we're at today from a Roush Yates engine perspective, we do count the number of wins. You can see the NASCAR Cup Series, Xfinity, Craftsman. You can also see the WEC Series, the IMSA. Again, a long, rich history of racing in various series. We have participated in other series such as ARCA and some other series that we do not count the wins. But again, through our long, rich development history, there's been lots of different series. I mentioned ARCA, but we also did Sprint 360s, we did 410s, we did off-road truck racing engines. So again, we have had a nice assortment of different platforms that we get to develop and test. The vision at Roush Yates Engines is to be world-class racing engines, a mission, design, develop, and manufacture championship engines in partnership with Ford Performance. And the core values really revolves around power, performance, and reliability. At Roush Yates Engines, there's 4 P's that we always talk about from a principle standpoint. The first one is our people. Without our people, we don't achieve the success. The other one is outside of people is processes, products, and even partners, right? Much like CONVERGE CFD, we really try to surround ourselves with individuals and partners that continue to push the envelope of innovation. Today's current lineup that Jamie will get more details into, but today we've currently raced the Ford FR9 carbureted V8 in the NASCAR Xfinity Series, which has 33 races in 2025. If you look at the Ford FR9 EFI V8 engine, that engine we raced in the NASCAR Cup, not only for Roush Fenway Kozlowski, but we do Team Penske, we do Wood Brothers, Haas Factory Racing, Front Row Motorsports, and Rick Ware Racing. So there is a good amount of teams that we're powering on almost every given Sunday. And also on the Xfinity side, we do power 5 to 6 teams. On the right-hand side is the Mark IV. We showed a little bit of this in the video itself. I'll let Jamie talk about engine development, but we did partner with Multimatic and Ford Performance on this adventure of where we leveraged the skill sets at Roush Yates Engines from design, development, and build of specialty engines in partnership with Ford Performance. Highlighting the series that we race in, starting on the left-hand side is that NASCAR Xfinity Series. The middle one is Daytona. That's the NASCAR Cup Series, winning races. It's important, but you can see how close the competition is. Then you can actually see a picture of that beautiful Mark IV card on the right-hand side. We have 3 facilities located in Mooresville, North Carolina. The facility that we're looking at now is the NASCAR engine shop. So again, that's where all the engine design and development and testing occurs. We do have 2 other facilities that are a support system. We have our internal 135,000 advanced manufacturing CNC facility itself. For there, we manufacture about 60% of the internal components that go into the FR9, but we've also went into some other areas of manufacturing and providing solutions. So not only today do we do the NASCAR engines and machine components for that, we also manufacture car components for the NASCAR Cup Series that we sell to all the teams. And from a diversity standpoint, we have moved into various military projects. We've moved into aerospace, we moved into medical, and today we even consider space a unique category that we manufacture and provide solutions to. This is a good bird's eye view of our CNC facility. Again, I think I might have mentioned AS 9100 certified, ISO 1345, 70 CNC machines. We continue to look at future investments, and future investments will be paired with some type of automation here. This is a pallet system that we have the capability of machining lights out, 36 pallet stations, tombstones there, and it's paired with 6 A61 Machinos. Before I turn it over to Jamie, right, for us, the business model really revolves around winning. So throughout our rich history, we have to make the business model work, but checker flags are super important. We have over 400 and some checker flags that are located in our facility, and it's a good way for us to capture the win itself and really some great memories of the success we've had since 2004. With that being said, I'm going to shift to the left to let Jamie move over and let us get started into a deeper dive of how we're leveraging the success of CONVERGE CFD each and every day.
Okay, great. Thank you, Todd. All right. All right, so myself, Jamie McNaughton, went to school at the University of Michigan as well as University of Wisconsin. After school, went to Ford Motor Company and did a lot of powertrain development activity there. And at that time, had an opportunity to go to Harley-Davidson, working on a joint venture project with Porsche on a V-Rod powertrain, and ended up doing several powertrains, design development test over the years for about 18 years at Harley-Davidson. I'm kind of an engine guy, enjoy engines, enjoy making power, enjoy the competitive side of the motorsports, as well as being efficient and with our engines as possible. All right, we'll talk a little bit around the evolution of racing engines, where we started, a little bit around our powertrain development activity, the power of our partnership with CONVERGE, and how we measure some of those successes, reducing time to track. And the more we do that, gives us opportunities to win with advantages. We'll go into a simulation case study as well, and talk a little bit around the future of simulation and engine development in general. So the evolution of Roush Yates Engines, NASCAR engines, as Todd spoke, in 2004, we had a combination of 2 of the best Ford competitors with Robert Yates and Mr. Jack Roush. We combined, and that brought us to an engine of the C3 builds. Now, of course, Jack had his best ideas of what made the most power. Robert and Doug had their best ideas of what made the most power. But between the two of them and creating a good 1 + 1 = 3 environment, we came out of the box really strong with that powertrain. But as you continue to develop engines, you find areas that we could do a little better. In the next series of 2005 to 2009, we went to the D3 powertrain. And then in 2009 to 2011, we went into our, at that time, next level FR9 powertrain that was carbureted still. And we currently run that powertrain configuration in our Xfinity classes. In 2012 and 2014, things changed. NASCAR went to EFI, and that required some changes to several components, but introducing EFI to that and then going around the efficiency improvements in EFI from carburation was a big step for us. We did another redesign, primarily structurally and in tuning benefits, if you will, for 2015 to 2018. And then another redesign of components on cylinder block and slight modifications of heads for 2019 to 2021. 2022, we're currently at our latest level in the platform that we are racing today. And overall, it's all about increasing performance and not compromising in durability. So we talk about performance and the testing capabilities that you need to really compete at this level. This is one of our fully automated test cells. And by fully automated, we mean everything that could be done on the racetrack, you need to be able to replicate here in the test cell. These differences include anything, environmentally, of course, pressures, temperatures, humidities, and then also some drivers drive a little bit differently than others. So some of the dynamics of driver style needs to be taken into account. And as a result, we will make dynamic modifications to some of the systems to ensure that we're not going to have any issues with any specific drivers, but yet not losing performance associated with those limits that could be set maybe a little bit differently for more aggressive drivers. We still need to make sure that everyone is going to have a reliable powertrain out there independent of their driving style. So anything that takes place at the track, we need to simulate here. We conduct a lot of performance testing as well as validation of durability requirements. We have tracks that are really short tracks. We have tracks that are really long tracks. And understanding all of those tracks and the types of powertrains that are raced at those becomes really key to us to be able to develop powertrains to the best of their capabilities. An example of just our mounting in the test cells that we have. One of the important things is making sure that this is exactly as it is in the vehicle. Sometimes you'll get feedback from the vehicle to engine mounting locations as well as temperatures under the hood. All of these structurally need to be identified, number one, and number two, make sure you're replicating those in your test cell as well. Some of that work that we do is learning, and how do we give back? So we give back to ourselves by improving engine performance and efficiencies, but we also give back to Ford Motor Company and other projects that are maybe not quite out to the level of refinement that we are on our Cup engines, but there's still a lot of learning that can be handed back to production-based powertrains on things that we do that can also help the production base as well. A lot of those learnings on the 3.5/3.8 liter track day supercars was knowledge transfer from work that we did on the Cup side. And as a result, that powertrain is a really good package. And we'll talk about that a little bit more. But great overall transparency between the race side and giving back to production. So on the design and development activity on our powertrains, what does a NASCAR engine really consist of? About 650 unique parts. And where do we get all these parts? Well, 1% of them are OEM supplied per the rules. We need to have blocks, castings, heads, castings, induction manifolds, and we also have a water manifold casting that comes from them. So out of the 650, we get these castings from Ford, and then we do pretty much everything else to design, machine, develop, and test for each one of our specs. That is our NASCAR Cup Series, which is the fuel-injected versions, as well as the Xfinity Series, that is the carbureted version. The Cup Series has two applications, a 510 horsepower super speedway application that we race at Talladega, Daytona, and Atlanta. Reason being that the power level is at 510 horsepower is just because of the speeds that those cars can go. And as a result, any more power than that gets dangerous for everybody. On the other Cup Series that we race is a 670 horsepower application that we run at pretty much all the other events, ovals, short tracks, road courses, all will run that engine spec. And you say 670 horsepower, what does that really mean? But that means different power curves for different types of tracks, different dynamic requirements for different types of tracks. Although it falls under one engine spec, there's a lot of differences associated with making that engine successful at each one of those tracks. 22 combined teams that we work with, and quality, of course, is key. We don't complain about something not working properly by somebody else or a powertrain part that has come in. Ultimately, we are the ones that are responsible for the quality of our powertrains to the teams. And in order to do that, we need to make sure quality parts are coming in the door, as well as our inspection processes and ensuring we're not going to have any issues. All falls under Roush Yates umbrella. Our development testing on our dynamic test cells, we talked about a little bit. We say, how much do you really have to find? So on the development activity, you'll be lucky to find, let's say, 1% increase in power over an entire year of development testing. That's how close we are. And as a result, let's say a 670 horsepower application, we'll round that to 7 horsepower. You're going to find 7 horsepower over the year. That's an awful lot of testing, an awful lot of very small gains that need to be found. And as a result of measuring those gains, you have to have a very accurate test cell repeatability to ensure that you're making the decisions for the right reasons. At 0.1%, you say, how can you do that, right? We need to ensure that data, processes, and people are the best that they can be, and also understanding what it takes to design, develop, test, and review data for these types of powertrains and the testing occurring. Our durability, we replicate everything that takes place on the track in our test cells, temperatures, pressures, humidity, as well as the type of drivers that are operating our cars. On the assembly and testing side, we build about 800 engines a year, and all of those engines are tested before they go out to the track. So what does that really mean, right? Every time a car goes out, we'll review data post-race, it'll come back, it'll return to the track, and it is thoroughly inspected and ensured that we're not going to have any issues the second time that powertrain is raced. A question might come up, how many times are these powertrains raced between complete rebuilds? It's 2, 3, sometimes 4 races before they are completely torn down again. But that's a function of the type of races that it's going to. And if there are any issues associated with some of the events that may put a question mark into the quality of the powertrain, but you can't go into it as far as we would like to because of the rules. There's a lot of data, post-processing, and learning that needs to take place on what that really means regarding integrity of the durability of the powertrain. So a lot of those engines, you can, the upper left-hand corner, you can see how those are transferred to the teams as well. Each one, again, performance tested and ensuring that we're delivering quality engines to them. When we're at the track, what really takes place? So we have practices, we have qualifying sessions, and sometimes there's not a whole lot of time to make any assessments on data before we go actually to the race. So what that means is a lot of data coming off the cars. We have to evaluate that very quickly. We need to look at the data to say, are we close to where we think we are for fuel economy predictions? Where are we at with drivability? A lot of that assessment comes directly from the drivers. Do we have any corner exit, performance not quite as smooth as you'd like it to be? Are there any changes or data that we see that is not lining up the way we think it should, and as a result could be a contributor to that? And then also, how does the engine feel? Power delivery, making sure it's nice and smooth coming out of the corners where you're grip limited everywhere. And the driver's doing everything they can to get the car around the track as quickly as possible. But in areas where you're grip limited, it's really important that we're delivering good, clean, predictable power as well. All right, that covers the high level on the engine development side. Why don't we transfer a little bit over to my design and analysis manager, Mr. Brad Tillich. He's been at Roush Yates for almost 2 years now. He has been doing engine simulation for about 25 years. So a lot of activity takes place on the simulation side here before we actually make parts. Of course, there's a lot of benefits to that, and Brad will talk about those more, but the more that we can simulate up front with software packages like CONVERGE, the less parts we have to make, the less tests we have to do, and the faster we can turn around good designs and hopefully get to the track faster with an advantage, as better products will come from this development and simulation activity. So here is Brad.
All right, thank you. Yeah, as Jamie said, Brad Tillich, simulation manager here at Roush Yates. Take some time here, describe what my group does and how we use CONVERGE in the engine development process. First and foremost, we build, correlate, and validate 1D, 3D, and coupled models. Basically, we continually validate 1D, 3D, and coupled models. Accuracy is everything for us. We will correlate a model to 24 high-speed pressure signals, 8 intake runners, 8 exhaust header pipes, and 8 in-cylinder pressure data sensors. We need the model to match the test and match the test for the right reasons. We'll often try to find a couple horsepower out of 700 in an already refined engine. Excuse me. And we want every cylinder to behave correctly for the right reasons over the RPM range. So takes a big effort to make all the high-speed pressure traces match well at all speeds and all cylinders, and that's what we spend a lot of our time doing. And so once we have that accurate model, we will provide direction to the design and development groups. We will provide explanations or understanding of results to engine development at Roush Yates, and develop processes to be faster and more useful to the development team here. We'll talk about a few different sections here. We have gas exchange, we have intake manifold, intake system, and we have exhaust headers. Thank you. Yeah, with gas exchange, with CONVERGE, Roush Yates has been able to obtain a much clearer understanding of the gas exchange process. Full cycle moving mesh simulations are becoming part of our regular engine development here at Roush Yates. The top figure you see here on the right is the start of a TDC overlap. Scavenging, which is often ignored in four-stroke engines, is very important to us. At at 8,000 RPM, it really doesn't matter to us whether the trap residual is 0.5% or 1%, because that can be a couple of horsepower and be the difference between a good valve event selection and a poor valve event selection. Let's see here. There we go. Of course, we do full cycle moving mesh simulations for the whole cylinder, but just for the demonstration here, we're showing an exhaust blowdown event. Let's see if I can play this again. Yeah. So we can make videos like this for a good understanding of what's happening. But more importantly, we can take cross sections throughout the exhaust ports, throughout the tailpipes. And that is actually what is used by the designers and developers to come up with the next design. Moving on to the intake system, we have a very complicated manifold. You see an example of that on the top right. Strict geometric constraints. Basically, we have all the openings that you see there are fixed in space. We have a dictated distance between the top of the manifold to the floor of the manifold. We have a controlled distance between the top of the manifold and the entrance to each of the runners. And most importantly, we have a casting that we have to stay within the limits of. So, and basically that is a casting approved by NASCAR, and that's not something that can be changed very easily. We have a restrictor plate that sits, looks like this. This is what limits the performance of our engines. It sits on top of the manifolds and will result in 4 jets. And at the high engine speeds, high power conditions, we do have more than 250 meters per second going through those holes and hitting the manifold floor. All the cylinders are highly coupled. Changes to one runner can significantly affect another runner. And fuel is everywhere. Unfortunately, we can't completely inject during valve open periods for best performance. So we have fuel in the manifold, fuel that goes from runner to runner, and it's something that mapping and calibration people have to deal with. And it's very important to optimize for both flow and tuning. Just another figure showing the complication of the intake manifold is kind of very large pressure amplitude waves in all of our runners, and of course they all combine in the common plenum manifold. And we have all of these interactions, and we have all the fuel and the jets, and we have to somehow capture that as best we can. In many cases with 1D, but then of course in some cases we have to bring in 3D in order to get to the accuracy level that we need. (1D) is very good at most of what we need to do, even on the intake side, but we do need CONVERGE to close the loop. We are looking for manifold deltas. We come up with a new manifold design. We are looking for deltas that are on the order of 0.25% to 0.5%. And of course, we don't make sure we don't point developers or designers to the wrong direction. Figures there show the performance deltas for 4 cylinders from a manifold swap. And if you can't quite see the scale, it's about plus or minus 0.5 horsepower for each of those cylinders. So it is in that 0.5, 0.6% that you see. And then we have kind of a representative port pressure comparison to test, simulated pressure to test pressure down at the bottom. Not every runner, every port, every speed looks this good, and so that's where we bring in CONVERGE. On the intake system, we use CONVERGE to simulate steady flow conditions. That's one of the things we do. So the CFD domain on one of our examples here, see here, goes from the restrictor inlet through the cylinder and replicates one of our flow bench setups. We have other flow bench setups, but we of course try to characterize the full intake system if we can. CONVERGE allows us to match flow bench data very closely and gives us clear views of velocity distributions at the entrance and throughout each runner. So we do get a number. We can be predictive with that number with CONVERGE, which is very important that we don't have to prototype and test all of these on the bench every time. And yeah, most importantly, we do get these velocity cross sections, which that's what we use, and that's what the designers use to make the next iteration. We can use this process. We get a new design, we evaluate in steady flow CFD, and then we evaluate in fully coupled 1D, 3D models, which we now have processes in place to do in just a day or two each. These are kind of fully coupled multi-cycle analysis of manifolds. Moving on to exhaust headers. As with the intake system, 1D can handle much of what we need for the exhaust system. You do see a CFD result here for our Xfinity exhaust system. We do have, as Jamie mentioned, two different series. We have a NASCAR Cup series, and in that case, it is a completely separate exhaust that leaves on opposite sides of the car. The Xfinity exhaust that you see here, at least part of the exhaust that you see here, crosses underneath and exits out one side. These again are good for demonstration, but the most important thing is that the CFD gives us more accurate high-speed pressure prediction at the exhaust ports. So that timing on the intake side and on the exhaust side, the use of CFD is primarily to make those predictions better, because once those predictions are better, we can have better confidence in the model, and of course better confidence in valve selections, and of course whenever we kind of deviate from the baseline model that we calibrate. Okay. There are some components which are complicated and difficult for 1D to fully capture on its own. We use CONVERGE to better characterize these, and as an example here on the right, you see some collectors in our exhaust system. And you can kind of see that the behavior of the collectors changes quite a bit based on what's happening at a particular time in the cycle. So this is something that's difficult for 1D to capture. Other things that we can use CONVERGE for in steady flow are multiple consecutive bends. You know, it's hard for GT does do bend losses, but when you have consecutive bends and they're arranged in weird angles, the bend loss is not accurate. So we can characterize these sections of the exhaust better with CFD. So we have a header design process, 1D DOE simulations with MLP models for weighted optimization. This is a case where we run 1D models, thousands of cases at each speed. We kind of do the weighted optimization to find the performance that we want for a particular race or a particular torque curve shape. We can then take that to a 1D, 3D coupling for a final check, and then, of course, move on to build and test if everything still holds up. So yeah, the future of simulation for RYE. First bullet point, we're more or less doing now, routine coupling for manifolds and headers. We will continue to do that and use CONVERGE again to get that better prediction port, intake port, exhaust port pressure predictions at all speeds, all cylinders. There's probably room in the future, or value in the future for being able to provide better information for calibration, part load operation, calibration, track specific information, race day conditions. this would of course be valuable to Roush Yates as well. You can imagine during a NASCAR season, there's large fluctuations in temperature. There can be large fluctuations in pressure, like this past season when NASCAR Cup Series went to Mexico City at 7,000 feet altitude. That was a calibration challenge. And of course, there are some tracks where we could give information to. There are tracks that provide no kind of ram boosting effect on the engine, and of course, there's tracks where we get a lot of that. Combustion optimization. Do this some, and we'll probably continue to do this in the future. Gas exchange and cylinder mixture motion, chamber design and combustion. And transients. We don't do a lot of transients now, but high-speed throttle transients to aid with engine transient calibration. If we are somehow able to help with transient fueling effects, transient AFR with throttle transients up and down, that would be very valuable to our team here. Yeah. So one more picture here near the end. This is the championship picture from 2024 and was our third in a row, I think, as Jamie mentioned. And of course, we'll hopefully have another here in less than 2 months. The 2026 look ahead with CONVERGE. Roush Yates and our Ford NASCAR partnership will enjoy the continuation of our relationship with CONVERGE to refine our engines, improving power and efficiency in the coming years. So yeah, that's all I have, and I think we'll open up to questions.